Welcome to the second day of the week. Sorry, the third day of the week. And welcome to the second lecture of Fabian on integrable models, and 1 hour and 25 minutes and 5 minutes of discussion.
Thank you. All right, so this is as far as we got yesterday. So before I carry on, were there any remaining questions that people wanted to ask before we move on? No? Yes?
So you kind of explain that you have a quench and then you see how it relaxes. So this approach is it equivalent when people study ETH in some Hamiltonian systems?
I'll come closer to ETH today.
Mm-hmm. So you have not still...
So this subsystem thermalization, as we have described it here, it's closely related to ETH, if you wish. And I'll just hold on a little bit. I'll come, I don't really discuss ETH in any detail, but I'll come pretty close. And okay. So if then...
But there is some distance between these two ideas still.
So ETH, well, I mean, in a sense, the ingredients I use here are the same as the ingredients ETH uses to some extent. So the main ingredient in ETH is this typicality argument, yeah, and that I also used. So when I when I was talking about this micro-canonical version of the steady-state density matrix, I basically said, well, so the energy eigenstates of local Hamiltonians, so Hamiltonians with local densities, have this very profound and important property that expectation values of local operators in these eigenstates up to finite-size correction actually don't depend on which energy eigenstates you take in a particular shell. And the same ingredient is the key ingredient also in one of the key ingredients in ETH. Yeah, so ETH goes a little bit further. So they also talk about off-diagonal matrix elements of operators, which is important if you want to discuss fluctuations. Just hold on a little bit. I mean, so if you're asking, is the set of assumptions larger or smaller in ETH or here, the set of assumptions is basically the same. Yeah, and the difficulty in proving these assumptions in a mathematically rigorous way is the same. It's very, very difficult to do because you have to be general. Yeah, so we'll come back to diagonal ensemble and things like that in a few minutes, and so if we can come back to that question then if you like. Okay.
So is there a similar equation like this one when you take simultaneous eigenstates of all the charges?
Yes, indeed there is. So this. As I said, well, okay, so basically what you have to do if you have conservation laws, higher conservation laws, which are local in the sense I discussed, this generally will not be true. Yeah, so if you only fix energy, yeah, and then calculate the expectation value of a local operator in energy eigenstates, in energy eigenstates where the energies are very close to one another, so they're in the same micro-canonical shell, the difference can be substantial. So what you have to do is a natural thing, and I do think I might discuss this today, I forgot. You have to fix not only the energy, so your micro-canonical shell is obtained not just by fixing the energy, but also fixing the values of the higher conservation laws. And in that shell, yeah, where now you have fixed not only the energy, also all the higher conservation laws. Now the states in that shell are simultaneous eigenstates of the Hamiltonian and all the higher conservation laws. And in these states, you have an analogous statement.
And it's again exponentially.
Well, so precisely what this behavior here is. I mean, so this exponential behavior in the thermalizing case is basically obtained by doing numerics. And so what it is for integrable models, to be honest, I'm not quite sure. Yeah, but so basically the difference would be a finite size correction, so something that goes away when you take the thermodynamic limit. So there is an analogous statement. Yeah, but as you would expect, you have to fix more than energy. Yeah, and then it's okay. And that ensemble, and I do talk about that in a little bit, so that's called the generalized micro-canonical ensemble, and that's the one we usually work with in integral models. Okay, so there don't seem to be any other questions or comments, so then let me carry on. So yesterday we got as far as here, so we basically looked at this particular example of the tight binding model, which we prepared in some initial state, which was some charge density wave. I mean, we had a particle on every other side. Then we looked at time evolution after preparing the system in that initial state, and we calculated single particle Green's function. We saw in real space, it did relax at late times to some statistical ensemble, which in this case is just some infinite temperature ensemble. Yeah, so this was the density matrix. And then by Wick's theorem, this gets lifted to all local operators. Yeah, and now another thing we can look at is the time evolution of observables, so of local operators. So one particular one just would be the density of fermions at site J as a function of time. Yeah. So initially, so that expectation value at time t equal to 0 would be 1 on all even sites and 0 on all odd sites, because that's how I had chosen the initial state. Okay, and now it's an elementary calculation, just using Wick's theorem. You can, not even using Wick's theorem, just using the Green's function I calculated yesterday. So you can work out what this expectation value is, and in the infinite volume limit, it's just given by this expression here, once again in terms of one of these Bessel functions. And I've plotted it for you here. So at time t equal to 0, as I said, on even sides, the expectation value is 1, on odd sides, it's 0. Yeah, and then as you time evolve, you see there are oscillations on the even sides, there are oscillations on the odd sides, but at late times, both expectation values settle to some time-independent value, which importantly is the same, and that's the point I want to make here, on even sides and odd sides. So I started in a state that broke a symmetry of my Hamiltonian, yeah, because it broke translational symmetry to translational symmetry by two sides. Yeah? But the Hamiltonian has full translational symmetry by one side. Okay? So you start out in an initial state which breaks the symmetry of the Hamiltonian. And what you see here for this particular observable, and you can check this is true once again using Wick's theorem for all multi-point correlation functions as long as they're local. At late times, so in the steady state, translational symmetry gets restored. So in other words, this charge density wave order melts, yeah, and in the steady state, the broken symmetry gets restored and you have the full translational symmetry. Now, does it always have to work like this? Well, so the answer is no. It has to work like this because I'm in one dimension. So here, the key observation is, I look at a one-dimensional tight binding chain. That's a one-dimensional model. And now, as you probably know, in one dimension, you can break discrete symmetries only at 0 temperature. That means in the ground state. But at any finite temperature, yeah, you're forbidden to break discrete symmetries. So this is somehow called Mermin-Wagner-Hohenberg theorem, although they didn't really. I said it's sometimes called Mermin-Wagner-Hohenberg theorem, so that's just the terminology. They certainly didn't prove this, yeah, but this is how people refer to it, yeah. So now, what does that have to do with the quantum quench and the steady state after the quantum quench? Because this theorem I just quoted, or this pseudo-theorem, once again, it's a true statement, but it's difficult to prove. I mean, you can motivate it very well, but prove it mathematically, you cannot do in general. Indeed, yes. That's correct. That's correct. That's correct. Exactly. Yeah, that's correct. So what does this Mermin-Wagner-Hohenberg theorem, or whatever you want to call it, have to do with what happens here? Well, think about it like so. So in your quantum quench, you deposit a finite energy density in your system, and that energy density is conserved. Now, finite energy density is like a finite temperature, morally. Okay. Even though I have here, in principle, to worry about conservation laws, it's a free theory. But at finite energy densities, typically, in one dimension, you cannot break discrete symmetries. And therefore, in all of these one-dimensional models, if you start in an initial state that breaks some symmetry, so typically, yeah, so there are exceptions, but I don't want to talk about the exceptions, I want to talk about the rule, these symmetries get restored. I have done it, actually. Oops. Yeah, I'm coming to that. You're jumping ahead. I mean, so you're too fast. Yeah. So this is my next. No, the next. I mean, I'll discuss this in some detail. Yeah. So let's come back. Okay. Okay, so this is the symmetry restoration in 1D. So now if you're in higher dimensions, 3 dimensions, or even in 2 dimensions with discrete symmetries, this simple argument I gave you doesn't apply. Yeah, because in higher dimensions you can have phase transition at finite temperatures, at finite energy densities. Yeah, and there you don't necessarily have to restore symmetries after quantum quenching. So this is a property of one-dimensional case. Okay, so now that finishes this explicit example for now. So now I want to move to the next topic, which we also have heard about already by various speakers during the last 2 weeks. So I want to talk a little bit about the spreading of correlations, and I think I even say something about entanglement. And in particular, the so-called light cone effects. So that's my next topic. And after that, I come to finite size effects and the things Alexios was asking about. Okay, so now it's always best to look at a particular example. So let's go back to our tight binding model where we know how to calculate everything. And I gave you this as an exercise, and I'm sure all of you have done it. Yeah. And of course, we'll check in the problem class today at 4 o'clock or whatever it is. Yeah. Okay, so let's look now at a particular correlation function, which is what I call the connected density-density correlation function. And let me just write down, for the sake of completeness, its definition. And I am tempted, it says do not cross. I mean, that's a challenge, so I will write it here. Sorry? So then it's not a challenge. Okay. So then I write it here. So the connected correlator is simply defined as the correlation function minus the product of the one-point functions. Okay, so that's the definition of this connected correlation function. It's very important in the following discussion that we look at this connected quantity. Yeah, that's absolutely necessary. Okay, so now this we can work out. I've done it for you yesterday implicitly. So if you look at these slides, I gave you an example how to use Wick's theorem for a 4-point function. This is a particular 4-point function. Yeah, and just substituting in the results for the Green's function we had derived yesterday, so you get this result for this connected density correlator. So once again, it's given in terms of some Bessel function. Now, all I do is I plot it for you using Mathematica. So here I put, I first of all fix k to be 1. Yeah, and then I plot this connected density correlator as a function of j and time. Yeah, and time has a dimension, so the dimensionless time is jt. J was this energy scale in my kinetic energy. Okay, so and what you see is a very clear horizon effect or light cone effect. So basically, this connected density correlator, if I go to a fixed separation between the two densities, which I look at, so let me take j equals to 20, then I have to wait quite some time before the density correlator, connected density correlations become sizable. Yeah, and you see the limit. Yeah, so the border of when these density correlations become appreciable, it looks like a linear function, like a light cone. Yeah. So now one has to be slightly careful. The connected density correlator outside the light cone is in fact not 0. It is not. It is just very, very small here. Yeah? And only after some finite time it starts becoming appreciable. Yeah? But this is not a strict light cone effect in the sense that the connected correlations would be 0 outside. And I say more about this in a little while. Yeah? And at what time does this light cone occur? Well, you can convince yourself. That's another exercise. So the light cone occurs at this time here. So it's related to the separation between the 2 points. And then this separation you divide by twice the maximal group velocity for excitations in this tight binding model. Yeah? So notice this factor of 2. So that's not what you would have if you look at horizon effects or light cone effects in equilibrium correlators. So the usual causality, yeah, in linear response theory, if you want, you just have a factor 1. So here you have a factor 2, and I will explain to you shortly why there's a factor of 2. There's a simple explanation for this. Yeah, and then the group velocity, of course, as usual, is just the derivative of the dispersion relation, which was just a cosine with respect to momentum. Yeah, and the maximum group velocity, you just take the maximum over all these velocities. It's 2j, and you can really check that reproduces the location of this light cone. Okay, so now this is in the particular example. Now, what's very important, this is completely and utterly general. You always have this. but you have to look at connected correlations. Yeah. Now, in my case, this light cone effect was very pronounced. You saw basically the connected correlators, it looked like it was 0, it was very small, and then all of a sudden it started taking off. That is not necessarily always the case. In my case, this was because the correlation length in the initial state was short. Yeah? I had a very, very short correlation length. One side. Yeah? I had a product state. And because of that, this light cone effect was very pronounced. Okay, so if I were to start in an initial state, which I can do, where correlation functions decay as a power law, yeah, in some critical theory, I mean, or in the ground state of some BCS Hamiltonian, something like this, well, critical BCS, I mean, it would have to be, if the correlation length was infinite, in other words, and I would have power law decay of correlation functions, there still would be a light cone effect, but it would be much weaker. Wouldn't be as apparent. Now, I added here something because Manas was talking about this in his talk. So he was very interested in these long-range models with long-range interactions or long-range hopping. And he was talking about light cone effects in such models. So let me kind of address what happens in the quantum case for models with long-range interactions with regards to this light cone effect. And precisely, it is, but with long-range interaction, long-range hopping. Yeah. So this is from a paper I wrote with some collaborators a couple of years ago. So if you want the details, you can look at it in the archive. So basically, we studied two models with long-range interactions. So one is a free fermion model, which you can solve exactly. So there you have pairing, some BCS-like term, and you have hopping, but the hopping I take to be long-range. And I take it long-range with some exponent alpha. And alpha can be anything. It can be small, it can be large, and I consider the effect of this long-range hopping for different values of alpha. Okay? And once again, so this is a free theory, so you can solve it exactly, which is the reason, of course, we studied it, because we can do everything in excruciating detail. So we also studied this model here, which is a long-range transverse field Ising chain, which is not integrable. Yeah, because if you rewrite this in terms of fermions, by doing a Jordan-Wigner transformation, so in this term, you pick up Jordan-Wigner strings, and you get very high-order terms involving fermions. So this is actually a strongly interacting theory, and you cannot solve it exactly. But the phenomenology as far as spreading is concerned, which is what I talk about here, is very similar in the two models, as I'll show you on the next slide. Now, the quenches we considered were very simple. So in this long-range transverse field Ising model, we start in the ground state for B equals infinity. Yeah? So where basically all spins point along the z direction, the ferromagnetic state. And then we time evolve with this Hamiltonian when B is equal to 1. That's the particular quantum quench. And in this long-range Kitaev chain, what we do is we start with delta over J equal to 10, and then time evolve with the Hamiltonian where delta over J is 1. Okay, and once again, we prepare it in the ground state of that model. These are particular quantum quenches. And now the question is, what do the light cone effects look like in these long-range models? Not in the examples I discuss here. So I can say something about the kind of thing you're asking a little bit later. So basically, in the protocol I've discussed here, you shake the system, so you do your quench, you wait, And any new phase, if you wish, in these examples would only occur in the steady state, yeah, at late times. So you can make new states of matter, and I can give you some examples if you wish, at very, very late times. So one example, let me just give you an example. So if you look at bosons in one dimension with attractive interactions, yeah, so just take bosons and put some delta function attraction. Yeah, so that system is not thermodynamically stable. Yeah, because basically what happens is all bosons pile together and form a big blob, and the energy is not extensive, etc. So there's no good thermodynamic limit. Yeah, but what you can do is basically start with non-interacting bosons, let's say in the ground state of non-interacting bosons, and then switch on suddenly an attractive interaction. Yeah, so that's a quantum quench. And then you look at time evolution, and eventually you reach a steady state, and that steady state now is perfectly stable. It's a stable state of matter in a model of attractive bosons, and that is a state which is very different from equilibrium states. Yeah. So that would be one example. So you can do this, but only at late times in the steady state. Okay. So now let me show you the light cone effect, which is really what I want to do. So here I always look at connected two-point functions in the transverse field Ising chain. I look at the connected two-point function sigma plus, sigma minus. And in the Kitaev chain, I look at just the single particle Green's function. Okay? Always at a distance d. And now the x-axis is the distance between the 2 points where I do my measurement, so to speak, and y-axis is time after the quench. And let's look at the first panel. The first panel is for long-range interactions, but long-range interactions which decay relatively fast. So 1 over distance cubed. So they are long range, but they decay fast. Yeah. So these models, like Alexius was talking about, so they typically have 1 over x squared. So here I have a power law decay, which is faster. And what you see a very nice light cone effect, because this is very similar to what we had in the nearest neighbor model. So if I fix the distance and I ask, when does my correlator become sizable? Well, it's first of all very small, and then at some point it takes off, and this front is basically propagating linearly. So for alpha equal to 3, certainly in these plots, it still looks like there is a good light cone effect. Yeah? Where the difference occurs is outside the light cone, so in this region, the behavior, so the correlators are very small there, but the qualitative behavior of the correlator is different in this long-range case compared to the short-range case. But it's not that important because it's tiny. Okay, so it still looks like a light cone. But now let me make alpha smaller. So this is alpha equals 3/2. So that already they decay quite slowly. And there you say, oops, there's not really any light cone effect left. Yeah. So if you look here, I mean, it's a very bizarre structure. You basically start having correlations at a distance straight away, and they cannot be neglected anymore. And if you make alpha very small, alpha equals 1/2, you see this effect is very, very strong. So there's no light cone effect there anymore at all. And that's not surprising. That's what you would expect, right? Because if you think about the Hamiltonian induces time evolution, right? And so your time evolution operator is u of t is e to the minus iht. So u of delta t, let's look at a very short time, is 1 minus ih delta t. Yeah. And then even if my two operators, which I calculate the 2-point function of, are very far away from one another, so let's say sigma plus of L, sigma minus L plus D. So if I do something like this, Yeah. So initially, so let's say I see this term. Let's say I don't get anything at time t equal to 0 or something which is very small. But then this term immediately will give a non-zero contribution because it contains terms which connect sides L and sides L plus D. So that's exactly what you would expect for long-range interactions. And so this is not surprising in a sense. What is more surprising, if you wish, is if alpha is large enough, then it looks like you morally still have a light cone effect, although, yeah. Okay, so what is the group velocity of the light cone effect? So that is an alpha-dependent quantity, this maximal group velocity. And I should have said, so this group velocity argument, that works for a free theory. So for this Majorana chain, I can do this. Yeah. So now this long-range transverse field Ising model, there are no quasi-particles. It's not an integrable theory. So an important question, a useful question in that context is, what is the velocity in that case? Yeah. And for integrable models, interacting integrable models, that question was answered by myself a few years ago. The answer is quite complicated, so I don't want to get into it. I can tell you afterwards privately. If you're not integrable, if you have some chaotic theories, still there will be a light cone effect. This is completely general, but what is the velocity? No. So what I'm looking at here are equal time correlation functions. It is. Yeah, but the out-of-time order correlator is just a completely different quantity. It's a non-equal time quantity. No, absolutely not. I mean, so what the statement I'm making, and I will explain where the light cone comes from in a moment, is in connected two-point functions, equal time two-point functions, after a quantum quench, there is a light cone effect. Always. You always find it. Well, you always find, for short-range interactions, you always find behavior like this. Well, you're asking something, what happens at very, very late times. Yeah? So typically, people have done numerical experiments, if you wish. So they've done numerical studies of quantum quenches in a Bose-Hubbard model, yeah, which is not integrable. Yeah? But nevertheless, they find a light cone effect, certainly at the time ranges they can access. So even though the model is not integrable. So there is a light cone effect in these things. So if you would ask what happens at very, very late time, so just observe, I here, the time range I consider is very limited. Yeah. So in the free theory, so this light cone would keep on going, but it would actually become weaker and weaker and weaker as you go up here. Yeah. And now, if you have a non-integrable theory, so let me just add a perturbation to this model which breaks integrability, which makes it interacting. You still have a light cone effect. So the main effect you see is this light cone, the intensity of the light cone. It drops off very, very quickly. Yeah. So basically, you see a clear light cone here, and then here it becomes very weak. Yeah. And then what you would expect if you wait very, very long, to very long times, to very late times, because the model is non-integrable, you would expect some kind of diffusive behavior. But that's a late time behavior. I'm talking here about the short time behavior. Okay? So you would see diffusive behavior, but in these numerical calculations for Bose-Hubbard models, if you wish, they simply cannot go to such late times. It's not possible. No. I mean, so we can talk about it later, but so there's a number of papers who have actually seen the light cone effect in the Bose-Hubbard model. And it literally looks like this, yeah. Okay, so that's light cone. So now where does it come from? So there's a nice physical picture that explains where the light cone effect would come from, certainly in free theories, also in integrable theories. And this picture is called the Quasiparticle picture, and it was proposed by Pasquale Calabrese and John Cardy, well, quite a long time ago now. And so the picture basically goes like this. So you do your quantum quench, yeah, and now assume you have a free theory like the one we have, or an integrable theory. So in those theories, you have stable excitations. Yeah, so I call these quasiparticles. And what the quench basically does at time t equal to 0, you create quasiparticles everywhere in your system. That's what the quantum quench does. And then, so that's at time t equal to 0. Yeah? And then subsequently, these quasiparticles, they have different momenta. Yeah? They start moving, they start propagating with some velocities. Okay, so you get a picture like this. So at time t equal to 0, you make these quasiparticles, and then they start moving to the left or to the right with velocities which have some range, but there is a maximal allowed group velocity. Because let's say I'm thinking about some lattice model with a nice dispersion. Okay, so now so that's the picture of what happens after the quantum quench. Now, what about measuring connected two-point correlation functions? So let's first look at one-point functions. So here O of R is some operator. So in my case, it was a density operator, and I was measuring a density at position R1 and the density at position R2 at some time t. Okay? So now this operator here, at that time, can get affected, it can get hit only by excitations, quasiparticles, that started in the interior of the backwards light cone of that operator. Okay, because particles out here, yeah, they don't have enough time, because the velocity is bounded, to reach that point up to that time. Okay, on the other hand, within this backwards light cone, the quasiparticles that get generated here, they can reach. Okay, so these operators at short times, yeah, so they basically get hit by quasiparticles from within the backward light cones, and this affects the one-point functions. Yeah, so it leads to what we call a dephasing of the one-point function. The one-point function had some expectation value at time t equal to 0, and because of this effect, they start now evolving in time and start decaying. So that's basically this kind of phenomenon. Yeah, it comes from the quasiparticles in the backwards light cone. Okay, now, if I wait long enough, if I basically wait until this time, so T star is the separation between the two operators I'm interested in, divided by twice the maximal propagation group velocity, the backward light cones touch, yeah, and then connected correlation functions can develop. Yeah, because now basically this spatial region here can affect both this operator and that operator. And then connected correlations start to develop. And the factor of 2 simply comes from the fact that you have 2 backward light cones, yeah, and the condition for connected correlations to develop is when they overlap. So that's the origin of the factor of 2. And the physical picture that Calabrese and Cardy basically put forward, they said, well, at time t equal to 0, what I actually do is, certainly for the initial states or they were interested in at that time, the quasiparticles were basically created in pairs carrying equal but opposite momentum. Okay, so where does this come from? I mean, so basically, what I said, my Hamiltonians, I want to be translationally invariant for simplicity. The initial states, I want to be translationally invariant for simplicity in the simplest case. So then the momentum in the initial state should be zero. Okay, and one way to get a state with zero momentum is you basically build it from pairs of quasiparticles with equal but opposite momenta. And for a variety of quenches in free theories, the initial state basically can be written as squeeze states, which are made precisely from such quasiparticle pairs. So you can write psi of 0 in these examples in this way: e to the sum over k, some matrix. And let's just say here alpha dagger of k, alpha dagger of minus k on some vacuum state. Yeah, and the time evolution operator in these examples could be written like this. Okay, and you basically see in this initial state, what you have done is you have created pairs of equal but opposite momenta everywhere. Yeah, so this is where this idea came from. And then these connected correlations, they basically get induced by entangled quasiparticle pairs. Because you create a quasiparticle pair here at time t equal to 0. One member of the pair, let's say, moves to the left with a given velocity. The other member moves to the right with a given velocity. And at time t, one of them hits this operator and the other one hits that operator. So that was their physical picture for this light cone effect. And an important ingredient of this is, of course, the existence of stable excitations, quasiparticles. Okay. Now, any questions about this? Yeah. No, it has nothing to do. So for the long-range chains, it doesn't have to do with the quasiparticles, if you wish. I mean, so okay. So as I try to explain here, if you have long-range interactions, no matter what the separation is between the 2 points, you do create necessarily connected correlations basically at infinitesimal times. Yeah, just do infinitesimal time evolution as I try to do here. So so this I basically would write as psi of naught, sigma plus L, sigma minus L plus D, psi of naught. Yeah, and then here you would have now, let's say, plus I delta t, and then psi of naught, sigma plus h, sigma plus L, sigma minus L plus D, psi of naught. Yeah, and now you see if I have short range interactions in my Hamiltonian, this commutator would simply be 0. Yeah, because these two operators are very, very far apart. Yeah, and there's no term in the Hamiltonian that would connect the two. Yeah, but if I have long range interactions, this commutator, even the first order, would be non-zero.
So is it like the group velocity? So there's a spread of group velocities, and you took the maximum
yes.
in the Majorana chain
yes.
problem, and that was finite, of course.
Yes.
And maybe
here it can be infinite, but it doesn't have to be infinite.
I see.
Yeah, it's simply this picture of propagation as we do here that implicitly assumes that your Hamiltonian is short range. Yeah. And if you're long range, there's a very kind of trivial effect in a sense, which immediately induces interactions. Yeah. Okay, so now there is a more, there's a mathematically rigorous way to understand some of these spreading things that I have been talking about, and that's what I want to consider next. So this is related to what's called Lieb-Robinson bounds, and so now I want to spend a few minutes talking about these Lieb-Robinson bounds. Okay, so Lieb-Robinson bounds come from a very famous paper by Elliott Lieb and Robinson in 1972. So they proved a theorem rigorously. What is the theorem? So they said, let's consider some non-relativistic quantum spin system with short-ranged Hamiltonian. So precisely the type of systems we have been talking about here. So an important restriction is basically the local Hilbert space should be finite dimensional. So like a spin and a half would be two states on each side. So that kind of stuff was important for them. Okay, and the Hamiltonian is short range. So that basically means the terms in the Hamiltonian density, they only connect close by sites. Okay, so then they say, now let's consider two spatially separated regions in this quantum spin model in d dimensions. I call them A and B. And the linear separation, so the distance between, the minimal distance between the two of them, I call L. Then, pick any operator OA that acts non-trivially only in this subsystem A, in this spatial region A, and any operator B that acts non-trivially only in subsystem B. Yeah, so you could take a spin operator here and a spin operator there, or a product of some spin operators here and a product of some other spin operators over there. So that's the kind of operators you consider. And the time-evolved operators are given as usual just by this Heisenberg picture operators. Yeah, so you conjugate the operator with the time evolution operator. Okay, and then in this situation, what Lieb and Robinson proved is a bound on the operator norm of the commutator between OA of t and OB of 0. Yeah, OA of t is the time-evolved one here, and OB of 0 is the non-time-evolved one there. Yeah, and that bound has a number of constants, which I don't really want to get into. So this are some constants which are related to the norm of OA and the norm of OB. The important factor is this one. So there's an exponential bound. So e to the minus L, which is the separation, minus some velocity, which is called the Lieb-Robinson velocity, times the time at which you evaluate this operator, divided by some length scale, yeah, which is xi. So the theorem is there exists a xi and there exists a v such that this following operator bound holds. It's a bound on operator, so it has nothing to do with states. It holds for any states, if you wish. Okay, so now how to think about this? Yeah, so if you think about this operator, so initially OA of 0 is a local operator. Yeah, so it has a finite support here. But when you time evolve it, the operator of course grows. Yeah, so the range of the operator then at any finite time, let's say this operator is no longer local. Yeah, because if you write down what OA of t is, so this quantity, you can write this as a sum involving multiple commutators. Yeah, commutators to all orders, and these commutators become less and less local. Yeah, so this is no longer a local operator, so this becomes big. involves the whole system. And so even if initially these two operators would commute, let's say they're spatially separated, eventually the commutator should become non-zero because this operator keeps on growing, keeps on growing, keeps on growing. And what the Lieb-Robinson bound basically is, it is a bound of the rate of growth of that operator. Yeah, so this operator, it gets tails. And the interesting thing is, according to these bounds, is that the tails are initially at least small. So that's a very, very cool theorem, actually. But importantly, it doesn't tell you what V is, it doesn't tell you what psi is. So, now let's try to connect this to light cone effects and the like. So this is the Lieb-Robinson bound. So now, No. I mean, so then you can try to basically work out what psi and v is in some cases, but so in general, this is just some velocity. Okay, so now let's look at the right-hand side. The right-hand side is exponentially small, yeah, because initially time t is equal to 0. You have e to the minus L over psi. So now if the spatial separation between these two regions is very, very large compared to psi, which is some kind of correlation length, then the right-hand side is tiny, yeah, and then the operators approximately commute. Okay, and what does that tell you? It basically tells you that if I make a perturbation in region B, it takes quite some time before it affects the spatial region A significantly. Yeah, so this is this operator OA of t, and basically it starts growing, yeah, as a function of time. And the important part, I mean, how do you say, it has tails everywhere, but it starts becoming big to some extent only within some light cone. That's the way to think about it. And measurements in A and B basically start affecting one another only after this light cone basically starts intersecting with region B. Yeah. Now, this looks like everything is causal in quantum mechanics, right? Because you make a perturbation here, and then you have to wait quite some time before you feel its presence over here. So it looks like quantum mechanics is perfectly causal. This is, of course, not true, because there is an exponentially small effect immediately. Yeah, so immediately you start feeling the perturbation. It's just its effect is exponentially suppressed in the separation. So you could say quantum mechanics in this sense is approximately causal. Yeah. No, this doesn't. Yeah. It basically no. I mean, you see, when you talk about gapped and gapless, you refer to some states, a particular part of the Hilbert space. This is an operatorial statement. This is like super duper strong. About operators. Yeah. So this tells you something completely independently of any state. Yeah, it literally tells you this operator OA, it starts growing. Yeah, but basically the tails you can bound. Yeah, so the tails, faraway tails, initially they're just tiny, and only at large time they start growing, and at some point you have to worry about it. Yeah, let me go through the next slide. I think that will, I wasn't quite sure whether I would need the next slide, but let me go through it. So, linear response theory. I mean, let's connect linear response theory to this Lieb-Robinson bound. Okay, linear response theory, you basically have some Hamiltonian which you like, H0, and then you switch on some infinitesimal perturbation at time t equal to 0, let's say. And then you want to ask, what is the response at subsequent times of physical observables to that perturbation you have switched on? So that's equilibrium linear response theory. So now I talk about states. Yeah? Okay, so I hope you remember this kind of thing from your whatever course it was. So quantum mechanics 3 or who knows what. Yeah. So it's a relatively simple exercise, and I hope you have done it at some point to show that if I look at the expectation value in any density matrix, in any state, of some operator OA, and I take this operator in the Heisenberg representation at time t, then this equals the same expectation value at time t equal to 0, minus I epsilon, a very small correction, that's the response of the system to the perturbation, times the integral from 0 to the time t, where t is the time at which I calculate this expectation value. And here you have the commutator between the perturbation and the operator you're interested in. Yeah, so that's a general formula from linear response theory, and so here would be the nonlinear response terms. And this is the expectation value in any density matrix. I can take the ground state, or I can take some finite temperature state, whatever. Okay, so now let's take it as our perturbation, just OB times the delta function of time. So basically what I do is, at time t equal to 0, I act with my operator OB. Yeah, so then what I just plug this in here. So then I get this equation here. Now you see the object I have in here is precisely the object Lieb and Robinson tell me about. Okay, so now what I basically want to do is I want to estimate the strength of this correction. How large is it? Yeah, it's always linear in the small parameter. Yeah. But Lieb-Robinson will tell me this actually as a function of t is negligible at short times. So now let me just calculate the absolute value of this piece to estimate its magnitude. And okay, so this is the absolute value of this expectation value in some density matrix. I just write it like so. You can also just keep some arbitrary state if you prefer. Now I write the density matrix simply as the sum over some probabilities, which add up to 1 times some states. I mean, so basically what I use here is that I can always write my density matrix rho as some probabilities times some one-dimensional projectors. And this is a complete set of states. So just plug this in here, so you get this expression. Okay. And then a simple inequality, so the absolute value of a sum is less than the sum of the absolute value. Yeah, so I get this expression here. And then what I can do is I can use Lieb-Robinson to bound this object by the Lieb-Robinson bound, and the n dependence drops out, and the probabilities add up to 1. And that basically tells me, due to the Lieb-Robinson bound, this piece here is exponentially small in the separation between the two operators at early times. And that precisely tells you, so if you make a perturbation in region B at time t equal to 0, you have to wait quite some time before, in linear response theory, you feel its effect at spatial region A. And observe that I use nowhere here what is the decay of correlations in my density matrix, in my state. Yeah? Did I? No, I don't think I did. Sorry, there's a typo here. Yeah. What I mean, what I mean is OA of t without the perturbation. Sorry. Thank you for pointing this out. So there's a typo on the slide. I did this late last night. So this is the unperturbed expectation value. Thank you for pointing that out. So this is literally the correction. Yeah. Thank you. Right. Now, what does that have to do with quantum quenches? So this Lieb-Robinson bound is just the operator bound on some commutators, but you can use it in the quantum quench context because if you have an initial state which is such that correlations in the initial state decay exponentially, so you have a finite correlation length in your initial state, you can prove, that was proved by Brahe, Hastings, and Verstraete 10 years ago, that the Lieb-Robinson bound implies an exponential bound on connected two-point correlation functions after a quantum quench. Yeah? And this basically tells you that outside some light cone, irrespective of whether your theory is integrable, non-integrable, whatever, connected correlation functions after a quantum quench, as long as in the initial state correlations decayed exponentially with some correlation length. So outside the light cone, connected correlations are exponentially suppressed at short times. So there is a kind of speed limit for, let's say, sizable connections to emerge after quantum quenches. Yeah, and this, unlike the qualitative pictures I was discussing before, so this is rigorous. Yeah, that's a bound. So questions about any of this? Yeah. Yes, absolutely. Yeah. So this was for short-range Hamiltonians, as I specified on the initial slide. So there are generalizations of bounds for long-range interactions. Some bounds were derived by Jens Eisert and collaborators a few years ago. So they are bounds, but they work quite differently. Yeah, and they have to, as we saw, because in the long-range case, you have a different phenomenology, as I showed for this particular example. Yeah. So what about physics? Yeah. So all of this was mathematics and kind of looking at models. Well, these light cone effects, of course, can also be seen in cold atom experiments. And so this, to some extent, also comes back to the question you asked earlier. So here are some cold atom experiments by the Munich group 5 years ago or something like this. So they did the following type of quantum quench. So they had a system of bosons. I think it was rubidium atoms. They prepared it in some optical lattice in one dimension. And they started with a situation you basically have some periodic potential. And initially, you have one atom sitting in each of the potential wells. Yeah, so that's not an eigenstate. And the Hamiltonian that describes the dynamics of the system is, to a very good approximation, this Bose-Hubbard model. So these are bosonic creation-annihilation operators that describe hopping of bosons along a line. And if two bosons occupy the same site, they repel each other with some strength U/2. Yeah? Okay, so they prepare the system in such a state, and then they okay, so then I think they let it settle, and eventually they do a quench on this parameter U from a very large value, so very, very strong repulsion, to a much smaller value. Okay, so they prepare it in some state. Let's say it's the ground state of the model at U0/J is 40. And then they suddenly ramp down the value of the interaction to a much smaller value. And the observable they measure some connected two-point function. And the connected two-point function is very similar to a density-density correlation function. It's not precisely a density-density correlation function simply because they cannot tell, they can only tell do they have an even number of bosons on a given site or an odd number. So they cannot tell experimentally whether they have 0, 2, 4, 6, blah, 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 atoms on a site or 1, 3, 5. Yeah. So it's not precisely a density-density correlator, it's a density-density correlator modulo this uncertainty. So they only know is it an even number of atoms or an odd number of atoms. Okay, so it basically has to do with how they image the system in order to extract the density. Yeah, and let's not kind of go into too many experimental details because that becomes murky for me. All right. Okay, so what they measure is this particular connected two-point function of operators which are related to the density operator just by this formula here. And that is plotted here as a function of time. And the different curves here are the connected correlation function of this S variable. Now, as a function of time for different separations between the two operators in your connected correlation function. And basically what you see, if the separation is large, then initially there basically is no signal, and then you start having a signal. And if you track the position of the first peak where the response of the connected correlation function becomes sizable, so it follows some kind of linear behavior at short times, yeah, which is what they study here. So there is in experiments also light cone effect. So this was the first experiment that I think measured this, but it has since been seen in many other experiments, as you might expect. Okay, so then now should I talk about this or not? So I discussed for you this quasi-particle picture for spreading of correlations. There is an analogous quasi-particle picture for the spreading of entanglement. Yeah. Well, as long as they remain local, that's important, yeah, which was the case. But basically, the connected two-point function of any local operator will have a light cone effect. That's what you would expect, yeah. And so the operator they measured in the end of the day was still local. It only involved the density at a given site, so it's okay. No, I mean, so basically, this NJ, yeah, well, okay. I mean, so it's not that complicated. Yeah. So it involves only NJ at that site. That's the important point. Nothing non-local about it. Yeah. Yeah. So what I mean is if you look at Sj of 0, it only involves Nj of 0, and then you time evolve that operator, and yeah. So, okay, so yeah, quasi-particle picture for entanglement growth. So let me have a go at this. Let's see how it goes. I mean, so not only correlation spread, also entanglement spreads. Yeah, and somebody asked me about the spread of entanglement yesterday, so I decided to include some of these slides. So let's see how it goes. So this is very similar to the quasi-particle picture for connected correlations, and was also developed by the same two people, Pasquale Calabresi and John Cardy. So again, starting point is a quench which creates quasi-particles at time t equal to 0, which start propagating with some velocities. And once again, let's assume that your quench creates these quasi-particle pairs with equal but opposite momenta at time t equal to 0. So the same starting point as for the connected correlations. Yeah, and now the idea they had is that entanglement spreads through the propagation of entangled quasiparticle pairs with equal but opposite momenta. So basically the idea is at time t equal to 0, you create a pair of quasiparticles at some position, basically everywhere in your system, but let's look at the pair here. It's entangled, this quasiparticle pair, and now when they start propagating, yeah, so they remain entangled at all times. Okay? And that then can induce entanglement between different spatial regions of your system in the following way. So the entanglement entropy, which measures, which is a measure for the size of the entanglement, which quantifies entanglement, so that would be the von Neumann entropy of a subsystem. So this is my subsystem B, and I want the question I ask is how strongly is this subsystem entangled with the rest of the system? Yeah. Okay. So now, how can these entangled quasiparticle pairs induce entanglement of this spatial region with the rest? Well, simply in the following way. So let's look at this quasiparticle pair. So initially it was made here. So now the left-hand member moves to the left, hits your subsystem at this time, whereas the right-hand member is in the other part. But they remain entangled. So basically this pair will contribute to the entanglement of B with the rest of the system at that time. On the other hand, this quasiparticle pair here, both of them actually remain within your spatial region B, so this quasiparticle pair does not contribute to the entanglement of your spatial region with the rest. So entanglement gets initially generated just around the boundaries, yeah, of your spatial region. Okay, and so now what Calabresi-Carty said, well, entanglement entropy is a measure of the number of correlated quasiparticle pairs such that at time t, one of them is inside B and the other one outside. Okay, so this was basically the postulate, and let's see how that works. Basically, so at short enough times, you can convince yourself that only quasiparticles in this spatial region can contribute to the entanglement entropy, because only for quasiparticles pairs created in this spatial region can one member end up in B and the other one outside. And the same here. And at late times, you basically see that only quasiparticle pairs in some spatial region of the same linear size as B can contribute, because outside they just miss your spatial region. So that basically tells you that the entanglement entropy of subsystem B with the rest of the system at time t should be now the integral over all momenta. So that you have to do is because group velocity depends on the momentum. So you have to integrate over all possible group velocities of the quasiparticle pairs. Some function which quantifies the entanglement carried by each pair, so we don't know what that is. And then this simple function which basically just counts the spatial region, the extent of the spatial region that determines where the range of where quasiparticle pairs can come from, such that they contribute to the entanglement of B with the outside. Yeah, so it's basically this at short times and this is at late times. Yeah. So you might say, okay, so that's very nice. So that's entanglement spreading. So what about this function f of k? We can actually fix this, interestingly enough. So the easy way to fix it is you just look at free theories. So there you can just do this calculation exactly. And what you find is this function f of k is related to the mode occupation number of these quasiparticles by this formula. Yeah. And motor occupation number of quasiparticles is given just by the expectation value in the initial state, because these quasiparticle motor occupation numbers are conserved in a free theory. Now, this formula should look familiar to you. So that's just the expression of the entropy density, thermodynamic entropy density. Yeah. And this now generalizes. You basically can say what you should put here is some function such that the integral over k over that function reproduces the entropy density, thermodynamic entropy density of your system at late times. And this then also suggests that the entanglement entropy actually does reduce to the thermodynamic entropy in the steady state. So that if you look at the time evolution of the entanglement entropy, you wait long enough, it just becomes the thermodynamic entropy density times the linear size of your subsystem. Yeah, so this would be some volume law. We call that because the entanglement entropy scales with the volume of the subsystem. This tells you what the limiting behavior is. So now Sasha will ask me, can you prove this kind of thing? So I can't prove it, but I can give you an argument that Sasha then can make in a proof. And the argument basically, and I probably just have enough time to do that, is like this. So let me look at the reduced density matrix after a quench. Let me, for simplicity, assume the system thermalizes. Makes the calculation a little bit easier. Okay, so rho B of t is the reduced density matrix of the subsystem after a quench. Yeah, and what I know is that the limit t goes to infinity, rho B of t, becomes trace B bar 1 over z e to the minus beta f times h. That's what we were discussing yesterday. So that's basically subsystem thermalization. It tells me that the reduced density matrix of the subsystem at infinite times after the quench becomes thermal. So it becomes the reduced density matrix of a Gibbs ensemble. Okay, so now the question is, let's look at this density matrix. Yeah. So what I'm supposed to do is I have a Gibbs density matrix, and I'm supposed to trace out the degrees of freedom outside my subsystem. So here I have my subsystem B, and I'm supposed to trace out these degrees of freedom. But now, importantly, in my steady state, I have a finite correlation length. Yeah? That basically tells me when I do this, this will be very close to a Gibbs ensemble for the subsystem. If B is large compared to the correlation length in the steady state. Yeah? And so where does this come from? Think of a path integral. So basically what you do is you integrate out the degrees of freedom outside your subsystem, but you have a finite correlation length. So the integrating out the degrees of freedom outside will affect only the boundary region, yeah, of this operator, this reduced density matrix. But inside, you basically don't modify the operator that you have there. So this we call the entanglement Hamiltonian. So you can formally, you can always express this reduced density matrix in this form. And let's do it like this. And the statement then is that HB is approximately equal to the restriction of H to B. Yeah, and the deviation you can bound. It's bounded by the correlation length, and this is the exercise. So, but that basically now tells you, as long as the subsystem is large enough, that the reduced density matrix after the quench is basically equal to the density matrix, not the reduced density matrix, but the density matrix of some Gibbs ensemble. Yeah? But the von Neumann entropy, so SB, is just of T, is just minus trace rho B of T log rho B of T. So that's a function only of the reduced density matrix of the subsystem. Yeah, but now when T goes to infinity, I just basically argued that this becomes a Gibbs distribution. So this becomes minus trace rho Gibbs B ln rho Gibbs B. And that is the thermodynamic entropy. Yeah, so it's an argument, it's a good argument, and I think it's possible actually to put this bounds by hand. Yeah, so H restricted to B, you mean? Yeah, so basically what I do is H is an Hamiltonian that acts on the entire system. So this is the restriction of H to the subsystem. So I simply throw away all the terms that take me outside the subsystem. Yeah? Okay, and so I think that is what I wanted to say about entanglement spreading after quantum quenches. And the next topic, but now it will be tomorrow, is finite size effects. And I think we leave it there. Thank you for your attention.
Correlation that you have even at small times outside of the light cone. It could be interpreted as a lattice effect, basically, as something that has to do with the fact that you have points on a lattice. Could you take the continuum limit in the following way? The speed of propagation should become large compared, at the time scales that you look, should become large compared to the lattice side. That means P times T that you're interested should be large compared to the lattice side. And in that limit, you should see the true continuum, which should have no such exponential correlations. The same thing happens whenever you have any lattice system, even a set of balls. You push one and immediately the last ball will fill it. But when you take the continuum limit, then you have a wave and that goes to zero.
Mm-hmm. Okay, twofold answers. First of all, I'm not sure. What I can tell you is, let me ask the same question in field theories. Yeah, so let me just go directly to a continuum theory. And let me ask, is there a Lieb-Robinson kind of bound for the Lieb-Leninger model? Yeah, delta function Bose gas. Non-relativistic non-relativistic phi to the fourth theory in 1+1 dimensions. Yeah? And the answer is no. No, but just a moment. I mean, so here I'm non-relativistic too. So I have a light cone in non-relativistic theories. I'm not relativistic. Yeah, so my dispersion relation does not start linearly. So it's quadratic, if you wish. So I have a non-relativistic theory here. There's nothing relativistic about it. So we call it light cone effect. If one wants to be more cautious, one should call it horizon effect or something like this. Yeah? But so it has nothing to do with relativistic invariance. And if I now look at the continuum theory, so Lieb-Robinson theorem doesn't apply because the local Hilbert space is infinite dimensional. So there you actually see in certain correlation functions you have a response, a sizable response outside the light cone. So that can happen. Yeah. And I think that's really what you were interested in, I suppose. Yeah.
Ramanujan. So about this entropy, so can you say anything about the laws of thermodynamics? Some first law, second law,
No,
can you say?
no, I certainly can't. No, no.
Even in the case of GG, can you say anything?
Okay, so the trouble is, if I judiciously stuck to a thermalizing system here where I only have a Hamiltonian, and the Hamiltonians I consider apart from this aside, I only put in because of manas. All my Hamiltonians are very short range. Yeah, and I need that the Hamiltonian is short range, because otherwise the entanglement Hamiltonian will not be well approximated by the restriction of the Hamiltonian to the subsystem size. Now the trouble is, if I have a GGE, I have not only the Hamiltonian, I also have the higher conservation laws, and they become less and less local. So Sasha will prove this. Yeah, he will put the bound with the correlation length for local Hamiltonians, but I think he would have to labor much harder for the GGE case. Yeah, simply because the operators you have here, they become by construction less and less local. The higher conservation laws have densities which involve more and more neighboring sites. Yeah, so then the answer is probably it can be done. So what I know is the answer is still correct, that I can give you the answer. I don't know how to substantiate it by a theorem which Sasha can put into a proof. So basically, if I have an integral model, yeah, so then I know I relax to a GGE. So then I know that SB of t has an infinite time limit. And so this becomes the von Neumann entropy of the macro state that describes my stationary state. Yeah, so basically the stationary state I can describe by a particular eigenstate of the Hamiltonian, all the higher conservation laws. So that's the generalized micro-canonical ensemble. And then I can describe this macro state using the Bethe-Ansatz methods, thermodynamic Bethe-Ansatz methods, and in particular I can calculate this von Neumann entropy. And that precisely gives me the infinite time limit of the entanglement entropy after the quench. So I know what the answer is, but it's not so easy anymore to get it in an operatorial way, starting from a generalized Gibbs ensemble.
I mean, so suppose you change the size of the system and consider some work for this system and argue the first law of thermodynamics. Is it possible?
I don't know. Yeah, so we can discuss afterwards. Yeah. No. This row is, let's say, some generalized mode occupation numbers that describe the macro state that characterizes the generalized micro-canonical ensemble. Yeah. So this involves the information about all the charges. Yeah, exactly. Yeah. So this encodes the information about all the conserved charges. This is not a thermal state. These are not the mode occupation numbers of a thermal state in the integral case. This would be the mode occupation numbers of some GGE. Yeah, and as I said, I know how to construct this. I probably won't have time to get to this tomorrow, but this was what my third lecture was supposed to have been about. Yeah, so I know how to construct this, and I know how to calculate the entropy of that macro state. Yeah, and we know from various sources that this holds. Yeah, unfortunately, this operatorial argument, which I think is actually quite good for the thermalizing case, becomes much less appealing in the GGE case for the reasons I have said. Doesn't mean one can't prove a theorem, but it is not going to be easy.
So I was hoping for some more clarification on the previous answer. I always assumed that the Lieb-Robinson bounds were a consequence of the locality of the Hamiltonian.
Yeah, but my Hamiltonian is local.
So in the case of continuum QFT, if you consider a local QFT, you're saying there's no sensible sense.
No, I mean, so you see, if we go back, yeah, so this is an important point, yeah. So here I said I have a short-range Hamiltonian and a finite-dimensional Hilbert space, and both of these are actually needed in the proof. And of course, you can ask, are they necessary? Can you generalize Lieb-Robinson to other settings? And people have tried. So now, what I can tell you, so there's some work, you can look at it, some explicit calculations in the non-relativistic phi to the fourth theory. So you basically have something like phi dt phi, and then L, something like this, and then you probably have something like minus grad phi squared minus lambda phi to the fourth. So non-relativistic scalar field, yeah, in 1 + 1 dimension. You can look at quantum quenches. Now, if lambda becomes very, very large, in that case, the model actually maps onto free fermions. And you can do some exact calculations. And in that case, there's some work by Calabrese, Kormos, and Colura. They just calculated exactly some density correlator, connected density correlator as I did. And they see they don't comment on this in their paper, but it's there, you can look at it. There is a sizable response at short times way outside the light cone in that case. So it's a counterexample.
So it's the lack of a local dimensional local Hilbert space, finite local Hilbert space.
In that particular case, yeah. So it's just a counterexample. That's all I can say. I mean, so one cannot just naively try to take it and try to apply it to other cases. What the limitations are, you have to ask somebody else. I mean, so there are people who do this for a living to prove Lieb-Robinson, Bruno Nachtigall and people, so they would be able to tell you about the state of the art. Yeah, I can basically just tell you, here is a non-relativistic field theory where Lieb-Robinson doesn't seem to work. Yeah.
Like a Q state local Hilbert space, and if you take Q to infinity, then you, on a lattice system, then you can still have...
It's the commutativity of limits, which is, as usual, the problem. Yeah.
Okay.
So in their proof, I mean, so you can have Q large as you like, but you have to keep it fixed. Yeah. And then if you take it to infinity, something goes wrong in the proof.
Because in this random unitary operator spreading, you can solve this problem in Q going to infinity limit, right? And then it kind of has these velocities. So even though you're taking it to infinity, Lieb-Robinson.
I agree, but it's a different quantity. It's a very different setting. Yeah. So if you think about it, I said it before, this is a super strong statement. It's an operator bound. I mean, independent of any state, I mean, in a sense, it's not surprising that you have to put restrictions on your system. Yeah, so also the only requirement in the operators is they're local, otherwise there's no requirement. I mean, so, yeah.
Okay, if there are no further questions, let's thank Fabian again.